Hi everyone, welcome back to my Itinerarium Chemistry YouTube channel. In this video, we will discuss about Werner's theory and also valence bond theory. Okay. First, we will start with Werner's theory. Werner's theory. Werner's theory was proposed to explain the formation of coordination compounds. It is based on the following postulates. Okay. We will see what are those postulates are. So, according to Werner's theory, central metal atom, okay, central metal atom, which shows two types of valencies. Central metal atom shows two types of valencies. Okay, first one is primary valency and second one is secondary valency. Secondary valency. Okay, coming to primary valency, here this primary valency is ionizable. Primary valency is ionizable. Here this primary valency is also called as oxidation number. Primary valency is also called as oxidation number of central metal atom, and primary valency is satisfied by negative ions. And coming to secondary valency, here secondary valencies are non-ionizable, which is also called as coordination number, Secondary valencies are satisfied by negative ions or neutral molecules, and secondary valency is directional. This results in the definite geometrical shape of coordination compounds. Okay, shape of coordination compounds. Now we will take an example, that is K4FeCN6. Okay, this is the coordination compound. Here this primary valency can also be written like this. Okay, and secondary valency can also be written like this. In this coordination compound, if you write the primary valency, we know that primary valency is ionizable, which is also called as oxidation number of central metal atom. Okay, and it is satisfied by negative ions. So first we will calculate the oxidation number of central metal atom. What is the oxidation number of central metal atom? Here +4 and here -4. We have 6 negative ligands, therefore -6. And what is the charge on the central metal atom? It is +2. Okay, therefore what is the primary valency? As I said earlier, primary valency is also called as oxidation number, therefore the primary valency is 2. Here the primary valency is satisfied by negative ions. Okay, here CN is a negative ligand, so which satisfies the primary valency, which is also called as oxidation number. Okay, next coming to secondary valency. What is the secondary valency here? So secondary valency is non-ionizable, which is also equal to the coordination number, and satisfied by negative ions or neutral molecules. Okay, so first we will identify the coordination number. What is the coordination number here? We have 6 CN ligands. Okay, 6 CN ligands are present. Out of 6 CN ligands, 6 donor atoms are attached to central metal atom. Okay, 6 donor atoms are attached to central metal atom. Therefore, the coordination number is 6. Okay, which is also called as secondary valency. Here, 2 is nothing but primary valency. Okay, here the secondary valency is non-ionizable, and we know that okay, the metal and the ligands which is present inside the coordination sphere is non-ionizable. Okay, therefore the secondary valency is non-ionizable. Here the secondary valency is satisfied by negative ions and also neutral molecules if there is any. Okay, here we have only negative ligand, so here in this case secondary valency is satisfied by negative ions. Okay, So once again, primary valency is ionizable, which is also called as oxidation number, satisfied by negative ions. Coming to secondary valency, here it is non-ionizable, which is also called as coordination number, which is satisfied by negative ions or neutral molecules. And here the secondary valency is directional. Okay, this is about Werner's theory. Next we will take reaction with AgNO3. Next we will take reaction with AgNO3. Okay, so first we will consider the coordination compound, which is COCl3 6NH3. Okay, when it is made to react with excess of AgNO3, the precipitate is formed. Okay, precipitate is formed. First we will write the coordination compound properly. Okay, here it is CO NH3 6 times. Okay, and outside the coordination pair we have Cl3, which is counter ion. Okay, when this coordination compound is made to react with excess of AgNO3, so what happens? So we know that the coordination entity is a non-ionizable species. Okay, so here outside the coordination pair we have 3Cl minus. Okay, so what happens? This Ag plus and NO3 minus, no, Ag plus reacts with 3Cl minus, therefore it is going to form 3AgCl, okay, which is a precipitate. Now if you measure the molecular weight, if you measure the molecular weight of AgNO3, what is the molecular weight of AgNO3? It is 143.5. Okay, here we have 3 moles of AgCl, that is nothing but 143.5 into 3, which gives you 430.5. Okay, next we will write the coordination compound, which is CONH3 5 times Cl. Okay, and outside the coordination pair we have Cl2. Again, when it is made to react with excess of AgNO3, again the same thing. Here we have Ag plus NO3 minus, and here we have Cl minus. Okay, so this Ag plus reacts with Cl minus to give 2AgCl. Okay, 2AgCl. Here why we have 2 moles of AgCl? That is because we have 2 Cl minus outside the coordination pair, therefore we are going to get 2AgCl. Okay, again we will take one more coordination compound, which is CONH3 4 times Cl2, and outside the coordination pair we have only 1 Cl minus. Again when it is made to react with excess of AgNO3, so again how many moles of AgCl is formed? It is 1 mole of AgCl is formed. Okay, again we will take one more example. Here CONH3 3 times and Cl3. So in this case we have no counter ion. When this is treated with excess of AgNO3, what happens? In this case we are not going to get any precipitate because we have no counter ion Cl minus. Okay, so no precipitate is obtained. Okay, based on this you may expect questions like they'll provide you the molecular weight and they'll ask you to calculate the number of moles of precipitate is formed. Okay, so like this also you may expect questions based on this, and we will take one more example and we will see what happens in that case. That is PtCl4 2HCl. Here how do you write the coordination compound? It is H2 PtCl4. Okay, this is the coordination compound. What happens when this is treated with AgNO3, excess of AgNO3? So no precipitate is formed. Okay, no precipitate is formed. Here there is no Cl minus as counter ion. Okay, we use AgNO3. Okay, in the confirmatory test for Cl minus acid radical. Okay, which gives AgCl. Okay, precipitate, which is Kurdi white precipitate. Okay, which is Kurdi white precipitate. This is about the reaction with AgNO3. Now we will go to molar conductance. Coming to molar conductance, Okay, so here this molar conductance, you can also call it as conductivity or conductivity. So we know that conductivity increases with increase in the number of ions. Okay, if you consider solution of ions, okay, solution of ions, consider Na plus and Cl minus. More the number of ions present in the solution, what happens to the conductivity? Conductivity increases. Okay, so here the same thing, molar conductance or conductivity is directly proportional to number of ions in the solution, number of ions in the solution. Okay, number of ions in the solution. So we will see how it is. Okay, first we will take a coordination compound, that is CONH3 6 times. Okay, here we have Cl3. So here what happens is this coordination compound, ionizes in the solution to give ions. Okay, so that is CONH3 6 times. Okay, so what is the charge here? It is plus 3 plus 3 Cl minus. Okay, so here this coordination compound ionizes in the solution to give CONH3 6 times, and the charge on the coordination pair is plus 3 plus 3 Cl minus. How many ions are produced here? Here 3 Cl minus ions, and here we have only 1 ion. So total how many ions are produced? 4 ions are produced. Okay, 4 ions are produced. And we will take another coordination compound, that is CONH3, okay, Cl, and outside the coordination pair we have Cl2. This coordination compound ionizes in the solution to give what? That is CONH3 5 times Cl plus 2 Cl minus. Here what is the charge on the coordination pair? It is plus 2. Total how many ions are produced here? Here we have 2 Cl minus ion, and here we have 1. Therefore total 3 ions are produced. Okay, next we will take one more example, that is CONH3 4 times Cl2, and here we have Cl. So again this coordination compound ionizes in the solution to give CONH3 4 times Cl2 plus Cl minus. Here the charge on the coordination pair is plus. Here totally how many ions are produced? 2 ions are produced. 2 ions are produced. So coming to first case, okay, here we have how many cations are there? That is 1. And how many anions are there? That is 3. Okay, therefore it is called as 1:3 electrolyte. Coming to second case, here we have 1 cation and 2 anions, therefore it is 1:2 electrolyte. 1:2 electrolyte. And coming to third case, here we have 1 cation and 1 anion, therefore it is 1:1 electrolyte. 1:1 electrolyte. By saying this, you can say that number of ions, okay, increases. Okay, the conductivity increases. Conductivity increases. Okay, here the number of ion increases, the conductivity also increases. Now the question is, what is the order of conductivity? Coming to first case, we have 4 ions, and in second case we have 3 ions, in third case we have 2 ions. Okay, so we know that number of ions increases, the conductivity increases. Okay, in the first case we have 4 ions, therefore A comes first, A, and then comes B, and then C. This is the order of conductivity. Okay, this is the order of conductivity. So you may expect this type of questions in competitive exams. Okay, now we will see drawbacks of Werner's theory. Werner's theory was not able to explain the following observations. Okay, so that is, Werner's theory not explained why only certain elements have property of forming coordination compounds. Next, Werner's theory fails to explain why secondary valency is directional, and Werner's theory fails to explain magnetic and spectral properties of coordination compounds. These observations are explained by theories like valence bond theory, crystal field theory, and ligand field theory. Okay, these theories will explain the above observations. Okay, first we will see what is valence bond theory. Now we will discuss about double salt and complexes. Okay, double salt and complexes. So here double salt means these are the salts which are formed by the combination of stable compounds, okay, in stoichiometric ratio, in stoichiometric ratio. For example, more salt, okay, more salt, so that is nothing but FeSO4 NH4 twice SO4 6H2O. Okay, this is nothing but more salt. Okay, when this salt is dissolved in water, when it is dissolved in water, completely dissociates into simple ions. Okay, it is completely dissociated into simple ions, completely dissociated into simple ions. Okay, simple ions. In this more salt we have Fe ions, SO4 and NH4 ions are there. So when this salt is dissolved in water, it dissociates into Fe2 plus, SO4 2 minus and NH4 plus. Here this salt is dissociated into simple ions completely when it is dissolved in water. Okay, now we will take complexes. Okay, complexes. We will take an example, that is FeCN6, charge is 4 minus. Okay, so here when this complex is dissolved in water, what happens? This complex do not dissociate, okay, do not dissociate into simple ions, that is Fe2 plus and Cn minus. Okay, this complex do not dissociate into Fe2 plus and Cn minus, whereas in double salt completely dissociated into simple ions when it is dissolved in water. Okay, this is the difference between double salt and complexes. We will take one more example, that is carnallite. The molecular formula of carnallite is KCl MgCl2 6H2O. Okay, when this is dissolved in water, it gives K plus Cl minus, okay, Mg2 plus. Okay, that means here this double salt is completely dissociated into simple ions. Okay, coming to valence bond theory. Okay, valence bond theory. Okay, so here the valence bond theory for the formation of coordination compounds is based on the following assumptions. We will see what are those one by one. Okay, first one is central metal atom provides vacant d orbitals for the formation of coordination compounds. Okay, and second one is central metal atom or ion used n-1d, ns, np, nd orbitals for bonding. Okay, next third one is geometry of the coordination compounds, okay, depends on hybridization. Okay, next one is pairing occurs in the presence of strong field ligands like CO, NO, Cn minus, NH3 and etc. That means in the presence of strong field ligands, okay, pairing occurs. Next one is magnetic moment. Okay, that is if number of unpaired electrons is greater than or equal to 1, then it is said to be paramagnetic in nature. Again, if number of unpaired electrons is equal to 0, then that is said to be diamagnetic in nature. Okay. Next we will see type of hybridization with respect to coordination number. Okay. Here we will write coordination number, and next to coordination number we will write type of hybridization, and then we will write geometry. Okay. First we will start with coordination number 4. Okay. For the coordination number 4, the type of hybridization will be sp3 or sd3. The geometry will be tetrahedral geometry. If you write the structure of tetrahedral geometry, it will be like this. Okay, here the central metal atom, okay, which is tetrahedrally bonded to the ligands. Okay, here we have a ligand, here ligand, and ligand. Okay, this is the tetrahedral geometry. Again, we will consider the coordination number 4. The type of hybridization is, it is dsp2 or sp2d. Okay, dsp2 or sp2d. Geometry is square planar. Okay, geometry is square planar. Here the d orbital involved in the hybridization is dx square minus y square. Okay. Now, if you write the square planar geometry, it will be like this. Okay. Here the central metal atom to which 4 ligands are attached to give square planar geometry. Okay. This is the square planar geometry. Next, we will consider the coordination number 5. Okay. Hybridization is sp3d. Okay. Hybridization is sp3d. The geometry is trigonal bipyramidal. If you write the structure of trigonal bipyramidal, so here is the central metal atom, and here 3 ligands are in one plane. Okay, 3 ligands are in one plane. One is above the plane and another one will be below the plane. Okay, this is trigonal bipyramidal geometry. Again, we will consider coordination number 5. The type of hybridization is, it is dsp3. Okay, the geometry is square pyramidal. If you write the geometry, here is the central metal atom, okay, and 4 ligands are in one plane and only one ligand will be above the plane. Okay, this is square pyramidal geometry. Next, we will consider the coordination number 6. Type of hybridization is, it is d2sp3. Geometry is octahedral. So if you write the geometry here, it will be like this. Here is the central metal atom. 4 ligands will be in the plane. Okay, and one is above the plane and one is below the plane. Okay, this is octahedral geometry. And again, we will consider the coordination number 6. Type of hybridization is sp3d2. Geometry is octahedral. Okay, here the d orbital is dz square and here the d orbital is dx square minus dy square. Okay, so this is about coordination number and type of hybridization and the geometry obtained. Okay, for the coordination number 4, 4 types of hybridizations are possible. One is sp3 or sd3, which gives tetrahedral geometry, and another set is dsp2 and sp2d, which gives square planar geometry. And coming to coordination number 5, again we have 2 types of hybridization, that is sp3d or dsp3. Okay, here sp3d gives trigonal bipyramidal geometry and dsp3 gives square pyramidal geometry. Okay, and coming to coordination number 6, okay, again here also 2 types of hybridizations are possible. One is d2sp3 and another one is sp3d2. Geometry is octahedral in both the cases. Now we will take some examples. Okay, before going to an example, let us note some points. That is, if unpaired electrons are present, then the complex is said to be spin-free complex. or which is also called as high spin complex. High spin complex. Okay. If unpaired electrons are present means the compound is colored. The compound is colored. Okay. Next, if there is no unpaired electrons, if there is no unpaired electrons, then the complex is said to be spin pair complex, spin pair complex, or which is also called as low spin complex, low spin complex. Okay, and here since there is no unpaired electrons, the complex is colorless. Okay, it is colorless. And one more thing is, in the presence of strong field ligand, in the presence of strong field ligand, pairing occurs. Okay, pairing of unpaired electrons occurs. Okay, in the presence of weak field ligands, okay, pairing will not occur. Therefore, no pairing. No pairing. Okay. So coming to strong field ligands, oxygen donors, nitrogen donors, carbon donors are strong field ligands. Okay, strong field ligands. And coming to weak field ligands, here halide donors are weak field ligands. Okay, this you have to remember. Magnetic moment of coordination compounds can be calculated by using spin only formula, that is mu is equal to root of n into n plus 2 Bohr magneton. Okay, Bohr magneton. Here n is equal to number of unpaired electrons. Number of unpaired electrons. Okay, let us take an example, that is nickel tetracarbonyl. Okay, here the central metal atom is what? Nickel. The atomic number of nickel is what? It is 28. So the outer electronic configuration is what? It is 4s2 3d8. Okay, here the oxidation number of nickel is 0. These are 3d orbitals. Okay, this is 4s and this is 4p. Okay, how many electrons are there in 3d orbitals? There are 8 electrons. Okay, so here these 8 electrons are filled according to Hund's rule. So here this Hund's rule says that in degenerate orbitals, okay, in degenerate orbitals like P, D and F, okay, electrons are singly occupied first. Electrons are singly filled first. Okay, and after that pairing occurs. Okay, so this is Hund's rule. So we have to fill the electrons according to Hund's rule. That means we have to fill the degenerate orbitals first with single electrons. 1 electron, 2, 3, 4, 5, 6, 7, 8. Okay, 8 electrons are filled in 3d orbitals, that is in degenerate orbitals. Okay, and next how many electrons are there in 4s? 2 electrons are there, therefore 1, 2. Here we have CO ligand, which is a strong field ligand. So in this case pairing occurs. Okay, in this case pairing occurs. Therefore what happens here? This unpaired electron is paired with this unpaired electron. Therefore again we will write the orbitals. Okay, this is 3d, 4s, 4p. Okay, so what happens? So here we have 2 electrons, here we have 2 electrons, here we have 2 electrons, and now this unpaired electron is getting paired with another unpaired electron. Therefore, here we have 2 electrons. Here 2 electrons of 4s orbital is promoted to 3d orbital, which is vacant. Therefore, what happens? Therefore, here we are going to have 2 electrons. Okay, how many ligands we have? 4 CO ligands we have. So each ligand donates a pair of electron, right? A pair of electron to the metal atom. So therefore what happens is, here 2 electrons are being donated by CO ligand, here 2 electrons, okay, here 2 electrons by CO ligand, and here 2 electrons by CO ligand. 4 CO ligands are donating 2 electrons each. Okay, so in this case, how many orbitals are involved in bond formation? Okay, 1 s orbital and 3 p orbitals are involved. 1 s orbital and 3 p orbitals are hybridized to keep sp3 hybridization. If you write the hybridization, what is the hybridization? It is sp3 hybridization. What is the geometry according to sp3 hybridization? It is tetrahedral. It is tetrahedral. Is there any unpaired electrons here? Okay, no unpaired electrons. No unpaired electrons. Okay, therefore it is a diamagnetic in nature. It is diamagnetic in nature, and this compound is colorless. This is colorless. Here you note down one point, that is, if n-1 d orbital is involved in bond formation, then that type of complex is called as inner orbital complex. Okay, inner orbital complex. Okay, if nd orbital is involved in bond formation, then it is called as outer orbital complex. Outer orbital complex. Okay, here inner d orbital is used. Okay, therefore it is inner orbital complex. It is inner orbital complex. Inner orbital complex. If you calculate the magnetic moment, that is mu is equal to root of n into n plus 2 Bohr magneton, where n is equal to unpaired electrons. So we don't have unpaired electrons, therefore n is equal to 0, therefore mu is equal to 0. You are supposed to identify all this for the given coordination compound. Okay, now we will take second example, that is nickel Cn4. The charge on the complex is -2. First, let us know the atomic number of nickel, that is 28. What is the outer electronic configuration of nickel here? That is 4s2 3d8. Okay, now we will calculate the oxidation number of nickel. What is the oxidation number of nickel here? Here we have Cn -4 and here it is +2. Okay, +2 -4 gives you -2. Therefore, oxidation number of nickel is +2. Now we will write the electronic configuration of nickel in +2 oxidation state. It is 4s0 3d8. Okay, 4s0 3d8. Now we will write the orbitals. Okay, this is 3d orbital. Here we have 4s and here we have 4p. Okay, so how many electrons are there in 3d orbital? 8 electrons are there. We have to fill the electrons according to the Hund's rule of maximum multiplicity. Therefore, it is 1, 2, 3, 4, 5, 6, 7, 8. Okay, 8 electrons are there. And here we know that Cn is a strong field ligand. Strong field ligand. So pairing occurs. Okay, pairing occurs. Here unpaired electrons of 3d orbitals are paired. We will write it again. It is 3d, again 4s, okay, and again 4p. Now we will write the electrons. Here 2 electrons, 2 electrons, and here also we have 2 electrons. Okay, we have 4 Cn ligands. Okay, 4 Cn ligands. Each Cn minus ligand gives 2 electrons to the central metal atom, right? Okay, so what happens? Here Cn, Cn, Cn and Cn. Okay, Cn ligand. So here 2 electrons, here 2 electrons, here 2 electrons and here 2 electrons. Okay, so what are all the orbitals which are involved in the bond formation? That is one d orbital and one s orbital and 2 p orbitals. Okay, therefore what is the hybridization here? Here the hybridization is dsp2. Okay, dsp2. What is the geometry according to dsp2 hybridization? It is square planar. It is square planar. Here we have no unpaired electrons. No unpaired electrons. Okay, therefore the complex is spin pair complex. Spin pair complex, which is also called as low spin complex. Okay, which is also called as low spin complex. And there is no unpaired electron, therefore it is diamagnetic in nature. Okay, and it is colorless compound, and it is colorless compound. Okay, and if you calculate the magnetic moment mu, that will be equal to 0 because we have no unpaired electrons. Okay, next we will take another example, that is COCN6. COCN6, the charge on the coordination pair is what? It is -3. Okay, so first we have to identify the atomic number of cobalt. What is the atomic number of cobalt? It is 27. What is the outer electronic configuration? That is 4s2 3d7. Now we will calculate the oxidation number of cobalt here. What is the oxidation number of cobalt? Here we have -6. Okay, -6, and the oxidation number of cobalt is +3. Okay, here +3 -6 gives you -3. Okay, therefore now we will write the electronic configuration of cobalt in +3 oxidation state. So therefore that would be 4s0 and 3d6. Okay, first the electrons will remove from the s orbital and then from d orbital. Now we will write the orbitals. This is 3d orbitals. It is 4s. Next comes 4p. Okay, now we will fill the electrons. How many electrons are there in 3d orbitals here? 6 electrons. Okay, so here 1, 2, 3, 4, 5 and 6. Okay, so we know that Cn is a strong field ligand. Cn is a strong field ligand. So here pairing occurs. Okay, pairing occurs. Therefore what happens? So here the unpaired electrons in 3d orbitals are paired. Okay, this paired with this unpaired electron, and here it pairs with this unpaired electron. Again we will write 3d 4s, it is 4p. Okay, how many electrons are there totally? 6 electrons which are paired. Okay, therefore 2 electrons here, here 2 electrons and here 2 electrons. Okay, so we know that 6 Cn ligands are there. 6 Cn ligands are there. Okay, each ligand donates 2 electrons towards the central metal atom. Okay, so what happens? Here Cn ligand donates 2 electrons. Here Cn ligand donates 2 electrons. Here 2 electrons are being donated. Here 2 electrons, 2 electrons, and here 2 electrons. Okay, now name the orbitals which are involved in the bond formation. That is here d2, okay, 2 d orbitals and 1 s orbital and 3 p orbitals. Okay, therefore what is the hybridization here? Hybridization is d2sp3, d2sp3. What is the geometry for d2sp3 hybridization? It is octahedral. It is octahedral. Okay, is there any unpaired electron? No unpaired electron. No unpaired electron. Therefore it is spin pair complex. Okay, spin pair complex, or which is also called as low spin complex, low spin complex. It is diamagnetic in nature and the compound is colorless. Okay, here magnetic moment mu is equal to 0, right? Next example is NiCl4. Okay, the charge on the coordination pair is -2. So first, what is the atomic number of nickel? It is 28. Okay, therefore the outer electronic configuration is what? It is 4s2 3d8. Okay, now we will calculate the oxidation number of nickel here. Okay, here 4Cl minus ligands, therefore charge is -4, and here the charge on nickel is +2. Okay, +2 minus 4 gives you -2. Now we will write the electronic configuration of nickel in +2 oxidation state. Therefore, it is 4s0 3d8. Okay, 3d orbitals, 4s, and it is 4p. Okay, 3d, 4s, and 4p. How many electrons are there in 3d orbitals? 8 electrons. That is 1, 2, 3, 4, 5, 6, 7, 8. Okay, 8 electrons are filled. We know that Cl is a weak field ligand, so that no pairing occurs. Okay, no pairing occurs. We have 4 Cl minus ligands. Okay, therefore we have 4 vacant orbitals provided by the metal. So what happens here? Each Cl minus gives 2 electrons, right? Each Cl minus gives 2 electrons, right? So here 2 electrons, here 2 electrons, here 2 electrons, and here 2 electrons. Okay, so what are the orbitals which are involved in the bond formation? That is 1 s orbital and 3 p orbitals are involved. Okay, 1 s orbital and 3 p orbitals are hybridized to give sp3 hybridization. Okay, therefore what is the hybridization? It is sp3 hybridization. Okay, what is the geometry for sp3 hybridization? The geometry is tetrahedral. Is there any unpaired electron in this system? Yes, we have 2 unpaired electrons. Okay, we have 2 unpaired electrons is equal to 2. Okay, therefore it is spin free complex, which is also called as high spin complex. Due to the presence of unpaired electron, it is paramagnetic in nature. Okay, it is paramagnetic in nature, and the compound is colored. Now I will calculate the magnetic moment, that is mu is equal to root of n into n plus 2. Okay, n into n plus 2. What is n here? Number of unpaired electrons. How many unpaired electrons are there? 2 unpaired electrons are there. Therefore, 2 into 2 plus 2. Okay, so what is the answer? 2.82 Bohr magneton. Okay, what is mu? Magnetic moment is equal to 2.82 Bohr magneton. Coming to next example, that is CrNH3 6 times. Okay, the charge on the complex is 3 plus. Here Cr is the central metal atom, that means chromium. What is the atomic number of chromium? It is 24. So what is the outer electronic configuration? It is 4s2 3d4. Okay, what is the oxidation number of chromium here? It is +3. Now we will write the electronic configuration of chromium in +3 oxidation state. Therefore it is 4s0 3d3. These are 3d orbitals, 4s, and it is 4p. Okay, how many electrons are there in 3d? 3 electrons are there. 1, 2, 3. Okay, 3 electrons are filled. Here we know that NH3 is a strong field ligand. But in this case, pairing not occurs. Okay, no pairing takes place. That is because pairing takes place to create vacant d orbitals. Okay, here already vacant d orbitals are existed. Okay, I'm repeating again. Pairing takes place to create vacant d orbitals, but here already we have vacant d orbitals. Therefore, here pairing will not take place. Okay, We have 6 NH3 ligands, right? Each ligand gives 2 electrons. Okay. Therefore, here 2 electrons, here 2 electrons, 2 electrons, and here 2 electrons. Okay. Each NH3 ligand gives 2 electrons to the metal cation. Okay. How many orbitals are involved in bond formation? Okay, that is 2 d orbitals, okay, 1 s orbital and 3 p orbitals. Okay, 2 d orbitals, 1 s orbital and 3 p orbitals are hybridized to give d2sp3 hybridization. Okay, what is the hybridization? That is d2sp3, d2sp3. What is the geometry here? Octahedral. Geometry is octahedral. Is there any unpaired electrons? Yes, we have unpaired electrons. How many unpaired electrons are there? 3 unpaired electrons are there. Number of unpaired electrons is equal to 3. Okay, therefore it is paramagnetic in nature. It is paramagnetic in nature and the compound is colored. Okay. Next one is due to the presence of unpaired electrons. Okay, it is spin-free complex. Or which is also called as high spin complex. Okay, here inner d orbitals are used in the bond formation, therefore it is inner orbital complex. If you calculate the magnetic moment, mu is equal to root of 3 into 3 plus 2, therefore mu is equal to what? 3.87 Bohr magneton. Mu is equal to 3.87 Bohr magneton. Okay. Now we will take another example, okay, which is important. Okay, which is important. That is CuNH3. The charge on the complex is 2 plus. Okay. What is the atomic number of copper? It is 29. So what is the outer electronic configuration? It is 4s1 and 3d10. Okay. Here what is the oxidation state of copper? That is plus 2. Now we will write the electronic configuration of copper in plus 2 oxidation state. Therefore it is 4s0 3d9. This is 3d, 4s, it is 4p. Okay. How many electrons are there in 3d? We have 9 electrons. Therefore 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, we have left with only one unpaired electron. So if there are two unpaired electrons, they undergo pairing. So but here we have only one unpaired electron. Okay, what happens in this case? It is NH3 4 times. Okay, I forgot. Okay, 4 NH3 ligands are there. So here pairing is not possible because we have only one unpaired electron. So for what we have studied, according to that, we should have the hybridization sp3, right? So here 2 electrons, here 2 electrons, here 2 electrons and here 2 electrons. Okay, because 4 NH3 ligands are there which gives 2 electrons each. Okay, so the expected hybridization is sp3, but experimentally it shows square planar geometry. Square planar geometry means the hybridization should be either dsp2 or sp2d. Okay, this should be the hybridization, okay, for the geometry square planar. Here we will be having 4d orbitals. Okay, 4d orbitals. So what happens is, here this one unpaired electron of 3d is shifted to 4d. That is, this is 3d. Here we have 4s. It is 4p. And here we have 4d. Okay, 4d. We will write the electrons now. Here 2 electrons, 2 electrons, here 2. The unpaired electron present in the 3d orbital is shifted to 4d orbital. Okay, so now what is the hybridization here? We have 4 NH3 ligands, right? So that the hybridization is what? It is DsP2. Okay, it is DsP2, right? So again, we are not going to get DsP2 hybridization, because if you write CuNH3 4 times, CuNH3 4 times, the charge on the complex is what? +2. When unpaired electron of 3D is shifted to 4D, what happens? Okay, it is ready to lose one electron and becomes CuNH3 4 times 3 plus. Okay, 3 plus. Okay, here what is happening? Plus electron, right? That means here oxidation is taking place. That means here oxidation is taking place, which is not possible. Okay, therefore, again, DsP2 is not the hybridization. So, according to the Huggins, okay, Huggins, here we have 3D orbitals, right? 3D orbitals, and here we have 4s, and then 4p, and then we have 4d. Okay, right? Okay, 4d. How many electrons are there in 3D? 9 electrons. Okay, so 1, 2, 3, 4, 5, 6, 7, 8. Okay, and the one electron which is unpaired will be remain in the 3D orbital. Now the orbitals which are available for the hybridization is one s orbital, two p orbitals, okay, and then one d orbital. Okay, it is one s orbital, two p orbitals, and one d orbitals are available for the bond formation. Okay, therefore what happens? 4 NH3 ligands are there. Each ligand gives 2 electrons. Therefore here 2 electrons, here 2 electrons, here 2 electrons, and in 4d orbital we have 2 electrons. Therefore, what are the orbitals involved in the hybridization? That is one s orbital, two p orbitals, and one d orbital. Therefore hybridization is what? sp2d. Okay, therefore what is the geometry here? Square planar is the geometry. Square planar geometry. Again, here the hybridization is what? sp2d. So here it is s orbital. Okay, here p2 means one is px and another one is py, and here d is dx square minus y square orbital. These orbitals are involved in the hybridization. Okay, here pz orbital is not involved in the hybridization, not involved or not participated, right? That is because here this pz orbital is perpendicular in nature. Okay, perpendicular, so that it is not involved in the bond formation. Okay, because it is perpendicular, so it is not involved in the bond formation. Okay, here the hybridization of CuNH3 4 times 2 plus is not sp3 hybridization and not dsp2 hybridization. The hybridization is sp2d, and the hybrid orbitals are s, px, py, and dx square minus y. Okay, this is about CuNH3 4 times 2 plus, which is very important, okay. Next we will take another example, that is MnO4 minus. Okay, here what is the central metal atom? Manganese. What is the atomic number of manganese here? It is 25. Therefore the outer electronic configuration is what? 4s2 3d5. What is the oxidation state of Mn here? Okay, that is x plus 4 into the charge on the oxygen will be -2, should be equal to -1. Therefore x is equal to what? It is +7. Now I will write the electronic configuration of manganese in +7 oxidation state. Therefore what happens? It is 4s0 and 3d0. Okay, first is 4s, okay, 4s, and then comes 3d, right? Okay, so now all the orbitals are vacant. So what happens is we have 4 oxygens. Okay, each oxygen gave 2 electrons. Therefore here 2 electrons, here 2 electrons, and here 2 electrons, 2 electrons. Okay, what are the orbitals involved in the hybridization? 1 s orbital and 3 d orbitals are hybridized to give sd3 hybridization. Okay, So therefore the hybridization is what? It is sd3. Okay, sd3. Geometry is tetrahedral, tetrahedral geometry. Okay, no unpaired electrons, no unpaired electrons, no unpaired electrons. Okay, if you write the structure of MnO4 minus, okay, it will be like this. Here oxygen, here oxygen minus, and here double bond O, here double bond O, and here double bond O. Okay, how many pi bonds are there here? 3 pi bonds are there. Okay, this is tetrahedral geometry with the hybridization sd3, with the hybridization sd3. Examples of coordination number 5. Okay, first one is nickel Cn 5 times. Okay, so here the hybridization is what? It is dsp3. Here d orbital is dx square minus y square. What is the geometry here? It is square pyramidal. It is square pyramidal. Okay, next we will take another example, that is FeCO 5 times. Okay, so it is dsp3 hybridization. It is dsp3 hybridization. Okay, here the d orbital is dz square. Okay, so the geometry is trigonal bipyramidal, trigonal bipyramidal. Here you note down that for the coordination number 5, two types of hybridizations are possible. One is dsp3, dsp3, and another one is sp3d, sp3d. Okay, so initially I forgot to tell this point. Okay, please make a note that for the coordination number 5, two types of hybridizations are possible. One is dsp3 and sp3d. Okay, third example, that is COOX thrice, and the charge on the complex is what? 3 minus. Okay, here the hybridization is d2sp3, d2sp3, which is diamagnetic in nature. Okay, which is diamagnetic in nature. Here the charge is 3 minus. Okay, here the charge is 3 minus. Now we will make note, that is platinum and palladium, platinum and palladium in Ml4. Okay, here oxidation state of metal is +2. Here it is plus or minus N. Here platinum and palladium in Ml4 plus or minus N type of complex. Okay, it gives square planar geometry. It gives square planar geometry with hybridization dsp2, with hybridization dsp2, irrespective of any ligand. Okay, irrespective of any ligand. Next one is, okay, Zn plus 2, cadmium plus 2, mercury plus 2. Okay, these metal ions with any 4 ligands, okay, with any 4 ligands, with any 4 ligands, always form tetrahedral geometry, tetrahedral geometry with sp3 hybridization, with sp3 hybridization, and which are diamagnetic in nature, which are diamagnetic in nature. And next one is 3D transition metals. Okay, 3D transition metals with oxidation state greater than or equal to 4, okay, or always form low spin complexes, or always forms low spin complexes, low spin complexes. Okay, and next one is 4D and 4D and 5D, 4D and 5D transition metals forms low spin complexes, low spin complexes, irrespective of any ligand, any ligand. Okay, these are the important points you have to remember. Okay, Now I will discuss about limitations of VBT. Limitations of VBT. Okay, limitations of VBT. The first limitation is nature of the strong field ligand and weak field ligand is not explained. Okay, nature of strong field ligand and weak field ligand is not explained. Is not explained. And next one is why strong field ligands, okay, pair up the electrons, but not weak field ligand, this is not explained by VBT. And the next limitation is it is not able to account for the spectral properties, not able to account for spectral properties. Okay, next limitation is in octahedral geometry. Okay, in octahedral geometry, bonds are of equal length. Okay, bonds are of equal length. Okay, but in the case of CuHO2 6 times, 2 plus. Okay, here if you write CO, here OH2, here H2O. Okay, all 6 ligands are H2O, right? So in this case, these 4 bonds are, okay, compressed and these 2 bonds are elongated. This is not explained by VBT. Okay, this is not explained by VBT. And also here VBT do not explain the kinetic and thermodynamic stability of the coordination compound. Kinetic and thermodynamic stability of coordination compounds. So these are all the limitations of valence bond theory. These are all explained by crystal field theory. We will see what is crystal field theory in the next video. If you found this video helpful, do like, share and subscribe. Thank you for watching.